Okay, hi everyone. Welcome to the Protocol Labs Research Seminar Series. Our speakers today are Greg Meredith and Christian Williams. Greg is the president of the RChain Cooperative. He's a mathematician and the discoverer of the row calculus, a co-inventor of the ladle algorithm, and the inventor of the toggle approach to graph theory. Christian is a mathematics PhD candidate at UC Riverside, conducting research in category theory with John Baez. Greg is going to talk to us about the role of types in refactoring the internet, and Christian will discuss structural type theory of higher order languages. They're kind of going to do a tandem talk. And ideally, let's hold questions to the end, maybe have a 5-minute, if there's any clarification questions after Greg's talk, before we launch into Christian's, but we want to make sure that we don't bleed into the second talk time. So with that, I'm going to hand it over to you, Greg, to take it from here.
Well, thank you so much. Thanks for having us. It's a delight to talk to interested and engaged parties. My talk is really just a setup for Christian's talk. So I'll be providing motivation and context and background, but kind of at a very rapid pace. Basically, I think a lot of us are aware that the internet is inexorably being refactored. So we're seeing a shift both in terms of the market interest and in terms of government interest towards decentralization, right? So just this week, I think the 4 heads of corporate state in the US were sitting down in front of a congressional panel. So that kind of gives us a sense of, you know, the seriousness of this. You know, of course, Europe has also weighed in on this. GDPR is not a small example of this push in certain ways. But in general, people are asking for decentralization, and blockchain is playing and will play a major role in that. But it's not going to do it by itself. There are going to be key technologies that fit together with blockchain to create generations of services that really were not imagined by Satoshi's stepchildren. So I'll talk about some of those services to kind of sketch out things that we might consider. So one of the interesting things is like how little known the revolution in logic is. So we're about 30 years into this massive revolution in logic. You know, at this point, I think a lot of people are comfortable with this idea of intuitionistic logic. Not every undergraduate who gets out of a math course today has been exposed to intuitionistic logic, but you know, if you are working in a particular sector in engineering, you probably become more comfortable with that. The idea of linear logic and the relationship between linear logic and modal logics are still very new to mainstream programming culture, for example. But it is well worth noting that logic has kind of long ago ceased to be, you know, the province of philosophers like Aristotle, and has become sort of the regular stomping grounds of, you know, electrical engineers and programmers and folks who have their hands dirty with the bits. But the revolution is still very much underway, and it's going to have consequences for all of digital culture. It's going to change not only the way we think about, for example, typing programs in programming languages. It's going to change the way we think about querying data sources. It's going to change the way we think about statistics and lots of other things. So notions of inference are going to change dramatically, and to the point where you know, what engineers do today will shift in a lot of different ways. So to make this a little bit more concrete, I want to just point out that code is kind of the dark matter of the internet, in the sense that, you know, when we look at massive repositories like GitHub, Bitbucket, and other things, it's a data asset. It's quite clearly a data asset. But the problem is that we can't search it in the same way that we search relational data. Right? So relational data, you know, like in the 60s and 70s, data storage was a bit of a Wild West kind of thing. You know, there were file-based stores and hierarchical stores, and, you know, finding the information that you stored was was a black art, and you had to go to people who understood, you know, arcane commands in order to see if particular facts were in the database. With COD and the discovery of the application of relational algebra to structuring of data, that all changed. And then, of course, I'm sure many people here have understood that there was a backlash against this in terms of this now decades-long dialogue between NoSQL and SQL. But none of those approach the real problem of how would we search for code on the basis of how it's structured and what it does. Right. And in fact, I probably, many people here might wonder, well, you know, is it even feasible to search code on the basis of what it does, right? Don't you run into halting problems and things like that? So there's lots of interesting math and engineering and science to do here. Right now, what we're currently working with is applying metadata and social techniques. So Bob knows someone named Alice who knows this library that does blah, blah, blah. If you do a little search on the internet, you'll discover that Hugel was developed over 15 years ago by some Haskell programmers who provided the ability to search the Haskell package system for programs that type checked according to a user supplied type, right? So this is beginning to connect the dots, right? So Curry Howard connects the dots between types and logic. We can talk about that later if you don't know what Curry Howard is, but we can effectively think of type systems as logical systems. And now we're using these types to effect queries. But the issue here is that the two functions, sort and shuffle, have the same type, right? So sort takes a list of some orderable domain like int, and that is randomized or somehow unsorted and produces a sorted list. Whereas shuffle takes a list that is ordered, at least potentially, and produces a randomized version of that list. So those are pretty much the opposite, and a query on the basis of that type is not going to be, therefore, particularly useful. You might ask if there are ways to improve that, but at the level of Haskell types, your queries still suffer quite a bit. There's a lot of desiderata. There's a lot of improvement to be had. But this revolution in logic that I'm talking about, and that Christian will make a lot more concrete for you, allows us to define types that are much more discriminating. So just to give some examples of harbingers of the kinds of things that sort of set up the work that Christian and Mike Stay and I have been doing, is the spatial behavioral logics of Luis Caires. So with the spatial behavioral logics, you can write down formulae aka types, that detect whether code is single-threaded, and likewise whether or not it's multi-threaded, and detect whether code can share secrets or code can deadlock. And we can use these kinds of formulae, aka types, to go and search repositories on this basis. So what we're looking at is the potential, were this to be realized in something like Hugel, for a complete revolution in the way we treat repositories like GitHub. And by the way, so to connect it back to blockchain, so smart contracting blockchains become the next generation of repositories, right? Because the smart contracts land on the blockchain and are there in perpetuity for at least the immutable blockchains. So if blockchain succeeds, they will be littered with smart contracts, and it becomes very interesting and important to us to be able to find those smart contracts. I'm looking for the financial model that I developed in 2018 that did this kind of thing, right? That sort of search becomes quite interesting when we're talking about extracting more value from the blockchain. Now, of course, one consequence of being able to search code on the basis of how it's structured and what it does is that we can get compilers to search code for new kinds of errors. So, for example, searching for multi-threaded code can be turned into a check for whether a code has a race condition. So, as a principal example, so I worked with Vitalik Buterin from 2015 through most of 2016. We were working on the Casper protocol together along with Vlad Zamfir and others. I warned Vitalik of the kinds of errors that Ethereum would be facing, and in particular, the kinds of errors like what was evinced with the DAO bug. As soon as the DAO bug came out, we rewrote it. Jack Peterson and I rewrote the buggy DAO contract in Rolang and typed it using the namespace logic types, which are similar, sort of have a family resemblance to spatial behavioral logics, and showed that the issue with the reentrancy issue in the DAO code becomes a race condition in a concurrent language, and our types would have caught it. So if you think about the implications, that buggy code would not have even type checked, therefore it wouldn't have compiled, let alone been checked in and deployed. So that would have saved the Ethereum community about $50 million and a lot of heartache. Okay, so also the search for code that shares secrets can be turned into a check for whether or not the code currently being compiled has a security error. And so these kinds of things obviously have import on the blockchain and lots of other code besides. But it also has implications to AI and code generation. So you can now think about an AI as assembling code from fragments that are scattered all over the internet. So you can imagine a user issues a query that gets turned into a type. The repository receiving the query is networked to a bunch of other repositories. It uses residuation, which is another kind of type calculation, to calculate the delta between the types of code that it has locally relative to the user's queries type, and then goes and forwards on the request for the sort of the leftover pieces from the residuation of the user's type and the types that are available. And that can also be used to rank particular solutions. This revolution is, of course, not limited to code. The reason for using category theory is that we can employ the techniques to generating these type systems for a very, very broad range of models of computation and information. So in particular, we can also apply the same approaches to things like Clifford algebras and other representations of geometric information. So this has applications to everything from self-driving cars to protein folding. You know, in 2010, I gave a talk, 4 Impossible Queries. One of the queries I proposed was find me all the wires running from the nose of the airplane to the midsection that undergo a twist. So you can write this kind of thing down in a type system derived from Clifford algebras. It also applies to dynamical systems such as cell signaling regimes. So I don't know if people are familiar with this. I did a lot of work with biologists in the early 2000s, early and mid 2000s. And there are a lot of boutique databases that capture information about cell signaling regimes. There are also a lot of databases about small molecules. So you can imagine a query of the form, find all the small molecules from that data source that when placed in this concentration in this cell signaling regime will prevent the signaling behavior from reaching a particular state, where that state is typically classified as a disease state. The short form of that kind of query is find a cure, find a small molecule based cure. So these are the kinds of queries that are expressible, made possible by the kinds of algorithms that Christian will be talking about. But I just want to talk a little bit more about the context, right? So the context is that as we have more blockchains like RChain that are scalable enough to hold public data, such as geolocation or healthcare data, then these queries make those data sources many times more useful and valuable. But it's also important to understand that, that we're talking about potentially very sensitive data that we don't want in the hands of a single party like, Google or Facebook or Amazon or what have you. Rather, we need to start thinking about what we might call, information utilities, in the same way that, electric companies, serve the public. Information companies can and should be thought of as serving the public. And so we want these kinds of capabilities not to be centralized, but to be in the hands of everyone they serve. And so that's kind of another reason why blockchain and decentralization sort of fits together with this, the kind of shift that the revolution in logic is going to apply. So that's really what I have prepared to chat about. I'm not sure what the time is right now. Oh, good.
We're doing great. Maybe if there are 1 or 2 very quick questions to clarify anything, I'm going to give you literally about 3 seconds to jump in before we kick it over to Christian. All right, Christian, you're up.
All right, thanks. Greg, do you want to speak?
Yeah, I'm going to stop.
Thanks. All right, hello. Thank you, Greg. Yes, so my name is Christian Williams. I am studying category theory with John Baez at UC Riverside. And for the second half of the presentation, I'm going to tell you more about the foundations of the type theory that Greg has been motivating, which I'm calling here structural type theory of higher order languages. So first of all, thank you very much for having us. I agree with Greg, and I'm sure as you all agree, this mission toward a distributive web is vital in these times. And I do think it will require deep coordination between theory and practice. So what am I doing here? I met Greg through Mike Stay, who also studied with John Baez, and they've been collaborators for quite a while now. And I'm very thankful to have been connected with them because I love math and I come from a math background, but in terms of social impact and how to actually improve the world, I think that math only becomes real through code. And I think, I just think that's extremely important, and I'm trying to transition into that sphere. So first of all, I'm curious, who here has learned about category theory, at least a little bit? A little bit? Okay, at least heard of it. If you've done some functional programming, you've probably used monads or heard about monads a little bit. Okay, so I know that category theory has a reputation of being abstract, and it's true, but it's mainly a matter of finding a good teacher, I think, and the community is definitely trying to get better and better about providing simple and clear explanations. The main thing I want to communicate about category theory is that it's not mainly a subject in itself, it's more a language and a perspective that is extremely general and versatile. And I think the utility of category theory is still greatly underestimated. So I hope to spark some interest and look forward to discussing it with y'all. So first of all, to clarify the title of this half of the talk, structural types are types that are built from term constructors and predicate logic. So for example, in the language of the natural numbers, you would have a structural type for being prime. A number is prime if it is not 1 and it's not the product of two things that are not 1, right? So this type is structural in the sense that it's only referring to the constructors of numbers, which would, in this case, would be 1 and the multiplication. So the idea of this work is to describe a way to take any formal language and automatically generate a structural type system with a lot of nice properties. And also in a way that is compositional, meaning if you had a translation between languages, it should also induce a translation between the structural type systems. And as Greg was mentioning, this system can be used to condition programs based on structure and behavior, and it doubles as a query system for code. So most of the talk, I'll mention the structural side, and then just at the end, I'll mention that we are working on this new behavioral side that expands it quite a bit. So one more question, who here has heard about K-framework? Okay, dot, dot. So it is a formal verification software where you can specify languages and then prove things about programs in a language. And it's become relatively popular in blockchain, especially in Ethereum, to prove that smart contracts do what you want them to do. And the reason I mention it is because the foundations of K-framework is something called matching logic. And the idea that I'm presenting now is very similar to matching logic. It basically has everything that matching logic does and more. And I want to motivate that from the category perspective, it's very natural and it just kind of falls out of the theory. All right, so here's the brief outline. So the main thing that I would hope to communicate is the idea that a programming language or any formal language is not only a syntactic thing, but it is itself one big structure. So when you present a language, so most of y'all are probably familiar with the BNF notation, this notation where you say, okay, what is, if you're describing the lambda calculus, for example, and you say, what is a lambda term? You say, okay, it's either a variable or it's the application of one term to another. or it's a lambda abstraction, right, to form a function. So computer scientists and programmers are probably the most used to this way of presenting languages, and then you give some equations at the end for beta reduction. That if you apply the function to a term, then you get the substitution. So category theory has a similar way, but it's arguably a bit more explicit in terms of the structure of what's going on. So the way that you would write this presentation using categories would be that application is a binary operation. You take two terms and apply them to each other. And then abstraction, you have to be a little careful. It doesn't just take a term, it takes a term with a distinguished free variable. So it's really taking in a function and then giving you a term where you pack it in using the lambda abstraction. So you can present any language this way. You present the constructors as certain operations, and you describe equations between them. And the idea of, one idea given from category theory is, so if you've never really heard about categories before, it's just a bunch of objects and arrows. It's a directed multigraph, but it also has the structure of composing arrows. So it's both a geometric and an algebraic structure. And the way that you can think about categories is that the objects are types and the arrows are programs that take in one type and give you another type. And that's exactly what we're doing here, and how you can make a language into an actual structure or mathematical structure. So
Christian, there's a question in the chat when you're discussing structural types, if this is the same use of the term structural types as in structural versus nominal types within category theory language.
Uh,
I don't think so. I think we'll have to check on
There's
that.
a relationship. So his types are structural in much the same way that structural. His types are not nominal, but they're richer in terms of the kinds of structures you can support.
Great, thank you.
Yeah. So the language of RChain is called the row calculus, and it stands for reflective higher order pi calculus. So it is a concurrent language, as Greg was mentioning toward the beginning of his talk, so that this operation here is a parallel. It puts two processes in parallel, and a program, rather than being a sequence of instructions, is a multi-set of parallel processes. And computation, rather than being sequential evaluation of functions, is about interaction between parallel processes. And I think that this is extremely important for the distributed web. I think that the history of computation has gotten entrenched in sequential computing for a lot of historical reasons, but to make a good distributed web, I think it's going to be essential that it's concurrent. And the main reason I think would be that the notion of communication is fundamental to concurrent languages. Rather than being an external notion out in hardware or something, communication is the fundamental rule of the concurrent language. And the way you can read this is, these are two processes in parallel. Somebody is sending on this channel A, and somebody else is receiving on channel A. And the one sending is sending some program. You can send arbitrarily complex pieces of code. And the one receiving has a program with a hole in it. And whenever they match up like this along some name A, then this code is turned into a message and plugged into this hole. So that's kind of the whole idea of the row calculus in that rule. So this is our motivating language, because concurrent languages, one of the main benefits is that you can express important properties of networks in the language itself. You don't have to use some external reasoning. So the big advantage of presenting a language as a category, where the objects are your context saying, okay, you got 3 processes and 2 names, and then 1 process with a hole in it. Those are your objects. And then the arrows, back to processes would be some way of taking that context and forming a process. The benefit of forming this category is that it makes the structure explicit, and then we can probe that structure for information. In particular, we can specify substructures of the code and use those as types. So for example, in analogy to the prime natural number, in network computing, it's useful to know if a process is single-threaded. So this would be that it is not the null process, the just do nothing process, and it's not the parallel of 2 non-null processes. So a process would be of this type if and only if it really is single-threaded. It's just a purely syntactic check. So a lot of the complexity of network computing comes from, a lot of processes in parallel trying to communicate on the same channel at the same time. And many algorithms would want to break that down into single-threaded processes and then build it back up piece by piece, checking for race conditions and that kind of thing. So our goal is to develop the language that we can specify these kind of types. So the main definition that's relevant to us. So once we make our language into a category, to study it, we want to assign sets of data to it. And so what I'm calling an indexed term set is a functor, just some kind of map from our category into sets and functions. So, so I'm calling it an indexed term set because it's not just a set of terms, it's a whole bunch of sets where for each sort in our language, we're getting some set of data. So it's a whole bunch of sets all together. So you plug in a context and you get some set of data that you could derive from that context. And the main insight that this work revolves around is that there is a natural way to take any sort of our language and turn it into a term set, which essentially is just a function that takes in some other sort R and gives you the programs from R to S. So you could think about this as representing all programs that have an output of kind S. And rather than being one big set, it's naturally indexed by what the input sort is. So the idea is that these are going to be our super types, and we carve out certain subsets of these to describe, kinds of programs that we care about. So, yeah, we're going to be interpreting these subsets of these term sets as our types, and use logical constructors on them, like in the single-threaded example. So this thing that I'm calling a term set, a category theorist really calls a pre-sheaf for historical reasons. And these form a very nice kind of category called a topos. And basically, it's this place where you have all the logic you could ever need. It's just a place with just perfect internal logic. So you get, for example, whenever you have a set, you want to think about the power set is the set of all subsets. So in this example, we can form the power set of any term set. And it's basically the same kind of construction, except we're dealing with indexed sets rather than normal sets. So given 2 subsets, or these sub things of a term set, we could form their intersection, union, implication, negation, all that stuff. And we also have quantification along maps. So we get all of predicate logic for free from this category of term sets. So the idea is, wanted to leave some space to draw. The idea is that we have we fix some sort in our language, and we're thinking about this term set that is just all programs of that output the sort S. And you can think about it as this giant tree with the bottom being S. And what we're doing is we're developing a language to specify subtrees, basically. So you would want to say, okay, I like these things coming from this sort, these things. Give me everything that's green and not red or blue. We're just developing this logic so that we can pick out certain subtrees to say, these are the programs that I like in this situation. So hopefully you can kind of picture it. So the other piece of the puzzle is that we need not only the logical constructors, but we also need the term constructors. So this par here, originally par was just some way to take two individual processes and put them in parallel. But now what we want to do is take whole subsets of processes, subsets of code, and put them in parallel. And to do that, for normal binary operations like parallel, it's not that hard. If you took two subsets, what does it mean to put them in parallel? It means you just take all pairs of something from one type and something from the other type, and then you apply the operation. So that's what this does, is it expresses the type of everything of the form, something from this type in parallel with something from that type. The harder question is how to do the same thing for binding operations like lambda abstraction, which are of a different form. They don't take in tuples, they take in functions. But the same thing is possible. It's just a little more complicated to describe. This is all in the paper. We don't need the details of how this works. But the point is that this way of lifting constructors of a language gives us this map from our language into these lattices. So you're sending each sort of your language to this lattice of types that are these subsets. And for each operation in your language, you're getting an operation between the lattices so that there's this correspondence between your original term constructors and your type constructors. And that correspondence is what we call polymorphism. We're getting that this type system is automatically polymorphic. So if we apply this to the row calculus, we get something that looks like the exact same signature as before, except now rather than operating on individual terms, we're dealing with whole chunks of code. These operations take in whole subsets. So it's just taking any language and beefing it up, just boosting it up to this higher level to help with reasoning. So using these, we finally have all that we need to describe this example type of being single-threaded. But really, we have a lot more. It's just kind of a first simple example. So I know I'm kind of out of time. The motivation, as Greg mentioned, was this framework called namespace logic. And so he wrote this paper soon after inventing the row calculus. And what it does is basically just take your language and add on logic and recursion so that you can do high-level reasoning about your language. And so just to give one last quick example of something that you can do in this logic. Two important properties of a distributed system are liveness and safety. So if we have some type alpha of names, so this would be some subset of the name sort in the language of the row calculus, and it represents, some set of names trusted by some system or organization. Then liveness would say that your system can always communicate on that set of names. And safety would say that your system can never communicate outside of that set of names. we can express that in this one-line formula. We can express this as a type that says, give me everything that can listen on alpha, and it doesn't listen, it can never listen on not alpha. And this recursion thing, I didn't have time to get into it, but we also get recursion for free. And what this says is not only on the first level does it satisfy this formula, but whatever it does next also satisfies this formula forever. So this is doing a lifetime check that something is remaining secure with respect to some namespace. And in effect, this is a compile time firewall. And a process will only be of this type if and only if it can always input on that namespace, and it can never input outside of that namespace. So this is just a quick example of how expressive the type system is. You can really write in a single line what is essentially a firewall that you cannot trick. It's just purely syntactic. And as I mentioned at the beginning, we are expanding this framework to now include behavioral types. There's a way of just like putting a graph of rewrites into these languages rather than having only equations. We can now talk about the process of computing one thing into another. And that expands this whole framework quite a lot. We get this generalized arrow type. Given any two types, you can specify the type of context so that if you plug in something of the first type, the result evolves in one step to something of the next type. So altogether, the framework is giving us this way to search or filter or classify code of the following form, but also code of the following behavior. So I'm very excited to start implementing this. Yeah, thank you for listening. You can find the paper on GitHub, and please feel free to contact me, and thank you.
Thank you, Christian, so much. That was fantastic. A little bit of virtual applause your way. I'm gonna open it up for questions. Please jump in with your questions and just dive right in there. Save me any need to edit out prolonged silences from the video. And if you find yourself having trouble jumping in because of conversation, just make a note in the chat that you do have a question, but I'll open it up now.
So I have, I guess, two top-level concerns about this sort of approach where that, for context, like the reference class that I come from is calculus of construction style theories, like you've funny for AGDA. So one is, it seems like this is a very syntactic style of type checking, and I don't know if all the semantic properties that you might want to check would happen to be in sort of encodable in a form of sort of just parsing the syntax tree and seeing if it has a certain shape. And the other thing I'm wondering is, can you have a program that outputs one of these structural types? Or is this more of like a validation type system that sits on top of programs but can't be used within a program?
Well, for the second question, I think it will be in the language itself. I think it will be a type system that you can write programs with. But for the first question, do you have an example in mind of a property that might not?
Yeah, I guess like Greg's example of you want to type check that a function is a correct sort of a list of integers.
Mm-hmm.
You need the behavioral pieces in order to get the rely guarantee types is what starts to give you the semantics. He's not, so Christian focused just on the structural bit because it's the easiest to explain. But essentially what we've done is we've lifted the rely guarantee kind of construction, which you find in session types and the Burger, Honda, Yoshida types to a much more general setting of all rewrite systems that have a particular shape. The other thing that you were asking, so there are lots and lots of type systems for which you have, principal types, but as soon as you but that works in computational settings where you have Church-Rosser. It doesn't work in situations where you don't have Church-Rosser. So you don't have Church-Rosser in the pi calculus, you don't have Church-Rosser in the row calculus, and so on and so forth. So calculating a principal type is kind of a non-starter. More importantly, it's not clear that in a concurrency setting you want anything like subject reduction. So it may not be the case that you want the property that once something has a particular type, it has that type forever. So in a setting where you're capturing behavioral information, that might not be the best choice.
Yeah, so I think you were talking about that example of like how to distinguish between sort and shuffle, because they have the same higher type, but they're clearly doing different things. That would be an example where you could use this arrow type, where you say, okay, what I really want is that it starts with something unordered. You could specify a type of some list being disordered, and that one might be weird, but you could certainly specify the type of ordered lists as a subset of lists of integers, and you would want to specify that sort is of the type that goes from unordered to ordered here, for example.
Also note that as you include more and more behavioral, it's really important to understand that there's a lot of knobs and dials on these kinds of systems. So as you get more and more behavioral information in your type, the likelihood that you reach halting hard gets higher and higher. So there will be cases where you've written down this really fancy spiffy type that says, yes, this is a bubble sort. It is exactly bubble sort, but you can't type check it in finite time.
Thanks for the question. More?
Yeah, thanks so much for both of the two halves of this talk. It was awesome. Building off of what you guys were just talking about, I think, if you want to do the sort of thing that Greg was talking about, where you're using these really sort of high level queries having to do with sort of the behavior of these programs, I think a big issue with a bunch of the taking exciting new math and applying it to these problems is that you end up with a language in which you can express just about anything you want, including these really high level ideas. But sort of computationally, when you actually implement them, it's hard to, it's hard to kind of get anywhere. What's kind of the right way to think about that, and why this is why the implementation is going to be sort of more practical to approach things this way rather than some sort of lower level expression of it?
That's a good question. I think that's one of the big questions. Greg, what do you think?
I agree with both of you. It's a very interesting question. So my hope is that for a very broad class of rewrite systems, you'll be able to give a specification of the operational semantics of the rewrite system and press a button, and the type system will along with the type checker, in fact, two flavors of type checker will pop out for you. One will be a model checking style type checker, where you're doing the kind of calculations that Christian is doing, and the other is a proof type, a term assignment style type checker, right? And that will have good correspondence between the two calculations, in the sense that that if it type checks one way, it's going to type check the other way. So my hope is that we do a once and for all encoding. We write down this. The reason we're using category theory is to structure that once and for all encoding, so that in general people aren't having to craft these by hand solutions. Just to give an example of how much the industry spends on these by hand solutions. Everybody knows JavaScript ain't typed, and that makes it really sucky for writing production code. That's why the big three have developed typed versions, right? Google has Dart, Facebook has whatever it is, I can't remember, and Microsoft has TypeScript, right? And so if you add up what they've collectively spent, it's near hundreds of millions of dollars on these by hand solutions. And our aim is to reduce that down to, well, it took me an afternoon to write down the operational semantics and then I pressed a button.
Yeah, that makes sense. That, like, especially, you know, if you have sort of a language that where you can sort of naturally express the sorts of higher level errors that you're looking for, like that definitely helps with model checking. I think, like, there's just this, and you know, if you can first run it through a proof checker before you run it through a model checker, then that also helps. So yeah, that makes a lot of sense.
Yeah, if you go to the GitHub for K-Framework, people in the community have been working hard to give formal specifications of entire languages. There's a whole specification of C++. And essentially, it is one of these categories. It can be interpreted as it's just a ton of operations and a ton of equations and rewrites. And the hope would be, you know, that you could just plug in that file and it produces a type system. It just produces this language that is C++ plus this structural behavioral type system.
So and there's, sorry to interrupt, but I did want to mention, so there's another avenue of work that we're pursuing, and only doing this right now in the context of the row calculus, but I believe this is also generalizable. So in the early 90s, Yoshida gave this brilliant decomposition of the pi calculus in terms of about 7 combinators. And then what she showed was if you take subsets of these, you get different fragments of the pi calculus with different expressive power. Okay, and you need all 7 in order to have the full, a complete computational system. So we've shown that you can take her trick, but what she couldn't get rid of was the new binder. So that was still kind of kicking around in the background of her combinators. So we showed with the row calculus, you can get rid of the new binder as well. So you get a handful of combinators, and then you can decompose the language into these fragments. So the thought is that you could restrict your type systems to only working on fragments. And the reason for that is so that you hone in on interesting decidable fragments where type checking becomes decidable, right? And if we can carry this out in this one case, then it might be possible to carry it out in other cases for more mainstream languages. But this is kind of the idea, is that you want to be able to twist the knobs and find these really interesting sweet spots where, yeah, the programs are very expressive, they capture a lot of design patterns that we're using in this domain, and the type checking is decidable.
Yeah, I was wondering, so, I mean, does the question of types enter into anything that Protocol Labs is doing? I mean, I was trying to learn a bit about IPFS and Filecoin. A lot of it's focused on very, practical issues. But does the question of type theory come in to stuff that, I mean, it probably, I assume. Does the question of like automatically generating a type system, is there any chance that would be helpful?
I mean, it definitely does with IPLD. I mean, I think like the way that we're sort of thinking, or the company's kind of thinking about what's going on right now is really building up the basis for the infrastructure to build some of this sort of higher level functionality into the web, right? And so with content addressing, you get some of what like Greg was talking about, right? Where you're able to sort of naturally reference blocks across all these different chains and projects and data structures across the whole decentralized web.
Yeah.
And then IPLD on top of that does let you, build these types manually, and is meant to be sort of a good basis for doing that kind of thing. But then that next layer, right, where you like take types that are expressed in IPLD and then use that to do something in some sort of framework, like the calculus that you're talking about, like that we are interested in building and like working on and doing research on and thinking about it, but haven't sort of done that at any sort of scale yet.
Yeah. Cool. What was it?
So
What did you, yeah.
I was just going to say, any last questions? We're coming up on the hour here, but feel free, Christian. It can be a question from you to us as well.
I was just, what was it? IPLD? What?
Yeah, I just put a link in the chat, and I can send you some stuff on it too. If that would help.
Okay, cool. Thanks.
Great. Well, thank you both for coming and spending some time sharing with us. This was really wonderful, and it is definitely a growing niche interest at Protocol Labs. So I think you scratched an itch of some of the attendees here. To those of you watching on YouTube, remember to like and subscribe if you want to suggest a topic or speaker. We have instructions on how to do that in the description. We'd also love to have you join our mailing list to receive quarterly newsletters, future talk announcements, information on future research funding opportunities from Protocol Labs. You can do this in the footer at our website, research.protocol.ai. Our next talk is this coming Tuesday, August 11th, from Sriram Kannan, who's from the University of Washington. He'll be talking about unified security analysis of permissionless systems. Same Zoom time, same Zoom channel. Thanks for joining, everyone. We'll see you next time.